Narcissus was a handsome Greek youth who was cursed to fall in love with his own image in a pool of water. It is said that Narcissus ultimately changed into the flower that bears his name, the narcissus. In those days, people obviously didn't have mirrors. So, Narcissus had never seen himself before he went and looked at himself in a pool of water. Most of us, though, use mirrors for personal grooming every day. However, not many of us know how we are able to see a likeness of ourselves in mirrors. The images that you see on a polished surface can be explained with the phenomenon of the reflection of light. Light from your body and other objects reflects from shiny surfaces, like mirrors, to form an image of those objects on your eye lens. At the end of this lesson, you will be able to define reflection as a property of light, define terms related to reflection, incident ray, reflected ray, and normal, state the laws of reflection, define images, identify the characteristics of images formed by a plane mirror, convex mirror, and concave mirror. Apply the mirror formula and sign convention to find out the relationship between distance of object and image from a mirror. When a ball is thrown at any surface, it bounces back. Similarly, when light rays are incident on a surface, they bounce back. The bouncing back of light rays thus is known as the reflection of light. Based on the nature of the reflecting surface, there are two types of reflections: regular reflection and irregular reflection. Regular reflection is caused by a smooth surface where all the light incident on the surface is reflected in a definite direction. Regular reflection is caused by plane mirrors, still water, and other smooth surfaces. Irregular reflection, also known as diffused reflection, is caused by irregular surface of the objects. The irregularity in the surface makes the incident light bounce back in different directions. Wood, wall, and other such irregular surfaces cause irregular reflection. Let us examine the phenomenon of reflection and the terms related with it. An incident ray is a ray of light incident on an object or a reflecting surface. A reflected ray is a ray of light that bounces back from a reflecting surface. The point of incidence is the point of an object or a reflecting surface at which a light ray is incident. Normal is an imaginary line drawn at the point of incidence, perpendicular to the reflecting surface. The angle of incidence is the angle between the incident ray and the normal, and is denoted by I. The angle of reflection is the angle between the normal and the reflected ray, and is denoted by R. Let us examine the properties of reflected rays by conducting an experiment. To begin, you need to fix a sheet of white paper on a drawing board. Draw a line MM' on it and mark a point O at the center of the line. Draw a normal ON on MM'. Next, draw IO, the incident ray, in such a way that angle IOM is less than 90 degrees. Place a strip of plane mirror vertically on MM'. Then fix two pins P and Q on the incident ray IO. P' and Q', which are the images of P and Q respectively, are observed from the other side of the normal. Two pins P1 and Q1 are fixed such that these two pins and P' and Q' are collinear. Remove the pins and draw a line OR passing through P1 and Q1 to represent the reflected ray. Now, if you measure the angle of incidence ION and the angle of reflection NOR, you will find that angle I is equal to angle R, and P, Q, P1, Q1, N, and O lie in the same plane. In other words, the experiment shows that the angle of incidence I equals the angle of reflection R. The incident ray, the reflected ray, and the normal all lie in the same plane. The property of reflection can be explained using mirrors. The laws of reflection affect our daily lives in many ways. In fact, we verify these laws every time we look into a mirror, which is a surface capable of reflecting sufficient undiffused light to form a likeness of an object placed in front of it. The likeness showed by a mirror is called an image. There are two types of images. Real images are the images that can be caught on screen. For example, the images projected on a screen or images taken using a camera are real images. Virtual images are the images that cannot be caught on a screen. Images formed in a plane mirror are virtual, as they disappear when the object is removed. Mirrors can be broadly classified into plane mirrors, which have flat surfaces, and spherical mirrors, which have curved surfaces. In this lesson, we will look at reflection in plane mirrors. Plane mirrors have flat, smooth surfaces. Plane mirrors are most commonly used for personal grooming, decoration, and architecture. These mirrors are constructed by coating silver on one side so that the other side can reflect smoothly. To see how an image is formed in a plane mirror, let us do an experiment. Consider an object in the shape of the letter P. From a point X on the object, consider a light ray incident on the mirror at point A. According to the law of reflection, the angle of incidence is always equal to the angle of reflection. Observe the angle of the incident ray as it reflects and travels to the eye. From the same point X on the object, another light ray is incident on the mirror at point B, and the reflected ray travels to the eye. The two reflected rays from A and B are divergent. When extended beyond the mirror, these rays meet at X dash. Thus, the image of the point X on the object is formed at X dash. Consider one more point Y on the object. A light ray from Y on the object is incident on the mirror at C, and the reflected ray travels to the eye. Similarly, another ray from Y on the object is incident on the mirror at D, and is reflected to travel to the eye. Like the two rays from A and B, the two reflected rays from C and D are divergent, and when extended beyond the mirror, meet at Y dash. Thus, Y dash is the image of point Y on the object. Similarly, rays from all points on the object are incident on the mirror. All these divergent rays are extended beyond the mirror to form the complete image of the object. You will also notice that the image formed in this case is erect, laterally inverted, of the same size as that of the object, and the distance of the image from the mirror is equal to the distance of the object from the mirror. These are standard characteristics of images of objects formed in plane mirrors. How will you verify whether the distance of the object from the mirror actually equals the distance of the image from the mirror? Consider two rays from a point object O, placed in front of a plane mirror. The ray of light, which incidents normally at point A, is reflected back along the same path. However, the second ray, which incidents at point B, is reflected along BC. This ray obeys the law of reflection such that N is the normal as shown. The reflected rays AO and BC, being divergent when extended beyond the mirror, meet at O dash to form the image. In triangles OAB and O dash AB, angles OAB and O dash AB are equal to 90 degrees. Also, based on the law of reflection, angle I is equal to angle R. Angles on alternate sides of the transversal on two parallel lines are called alternate angles and are always equal. Here, angle I and BOA are alternate angles. Therefore, angle I equals angle BOA. Angles in similar locations with respect to a transversal on two parallel lines are called corresponding angles and are always equal. Here, angle NBC and angle BO-A are corresponding angles. Therefore, angle R is equal to angle BO-A. Therefore, angle BOA is equal to angle BO-A. Using the angle, and side property of equal triangles, we can say that triangles OAB and O-AB are equal. Equal triangles have equal sides. Therefore, OA is equal to AO', which means that the distance of the image from the mirror is equal to the distance of the object from the mirror. Let us switch to another aspect of images in mirrors, the relationship between the mirror and the image size. You may have noticed that not all mirrors enable you to see your full image. You typically need a tall mirror to view your full image when getting ready to go somewhere. This is why most bedrooms sport tall mirrors called full-length mirrors. Clearly, image formation is affected by the size of the mirror. A simple experiment can help you determine how tall a mirror you require to view your full image. Consider a person of height HF standing in front of a mirror on the wall, where H represents the highest point on his head, F the lowest point on his feet, and the IE at eye level. The person will be able to see his full image if he can see points A and B. The mirror requires a height where the incident rays HM and FM after reflection reach the eye of the person. These will form an image H', F' when produced backwards. In triangle HEH', AM is parallel to HE, and A is the midpoint of HH'. Therefore, M is the midpoint of H'E. Similarly, in triangle FEF', NB is parallel to FE, and B is the midpoint of FF'. Therefore, N is the midpoint of F'E. Now in triangle H', F'E, M is the midpoint of H'E, and N is the midpoint of F'E. Therefore, MN is parallel to and half of H', but H', is equal to HF. Therefore, MN is equal to half of HF. Thus, in order to see his full-length image, a person requires a plane mirror that is half his own height. Therefore, to view the complete image of an object, you need a mirror that is at least half the height of the object. Kids sometimes use mirrors as playthings, where they rotate the mirror in the sunlight to make the sun's rays reflect on another person or an object. Suppose a child uses a mirror to direct the sun's rays to a friend standing at a window on the first floor. Now he wants to direct these rays to another friend standing on the road some distance away. If the lines joining the boy to the two friends make an angle of 120 degrees, by what angle should the child rotate the mirror? To solve this problem, let us see what happens to a reflected ray when a mirror is rotated through an angle. Consider a ray of light IO incident on a plane mirror in position M1, M2, such that OR is the reflected ray and ON is the normal. Therefore, based on the laws of reflection, angle RON is equal to angle ION. which is the angle of incidence I. Therefore, angle IOR is equal to twice the angle of incidence. Let the mirror be rotated through an angle theta about point O, so that M1', M2' is the new position of the mirror, and ON' is the new position of the normal. The position of the incident ray remains the same, but the new angle of incidence is angle ION'. Angle ION' equals I plus theta. Let OR' be the reflected ray such that angle N'-OR' is the new angle of reflection. From the figure, you can see that angle IOR' is equal to angle ION' plus angle N'-OR'. Substituting ION' and N'-OR' in terms of I and theta, you get angle IOR' is equal to 2I plus 2 theta. Subtracting equation 1 from equation 2, we get angle IOR' minus angle IOR is equal to 2I plus 2 theta minus 2I. Therefore, angle ROR' is equal to 2 theta. Thus, for a given incident ray, if the plane mirror is rotated through a certain angle, then the reflected ray rotates through twice that angle. Hence, for the given problem, if the child has to direct the rays to a person standing 120 degrees apart, he has to rotate the mirror through an angle that is equal to half of 120 degrees, that is 60 degrees. Have you ever wondered about how images are formed in a kaleidoscope? A kaleidoscope uses 3 mirrors placed at an angle to produce multiple images. When mirrors are placed at an angle, the reflected ray from the first mirror is incident on the second mirror. The second mirror in turn reflects it back to mirror 3. Thus, multiple images of the object are formed. The number of images seen in such an arrangement can be calculated using the formula N is equal to 360 divided by theta minus 1. Based on this formula, if the angle between the mirrors, theta, is 90 degrees, then the number of images formed is 3. Experimenting further, if 2 parallel mirrors are placed with their reflecting surfaces facing each other, the mirrors form an infinite number of images between them. This is because the angle between the mirrors placed in this manner is 0. Mirrors can be placed at angles to change the direction of light received by the eye. For example, 2 mirrors placed at specific angles are used to make optical instruments like periscope. Periscope is used in land and sea warfare, submarine navigation, and elsewhere to enable observers to view their surroundings while remaining under cover, behind armor or submerged. A reflecting periscope consists of 2 mirrors to change the direction of light coming from the scene observed. The first mirror deflects the light down through a vertical tube. At the bottom of the tube, another mirror is placed at an angle to reflect the light towards the observer's eye.